Greetings, my name is Patrick Soucy. I work at INRS in Quebec, Canada, where we have a small microscope facilities which have been modified with lasers and also a dual beam. The TMs are GL with lasers from different manufacturers, with one operating in the nanosecond scale and the other at the femtosecond scale. But that is not very important right now. We're just going to be talking about the dual beam instrument, which is a Lyra 3 from Tescan. This scope has a Schottky electron gun and a gallium ion gun. It is equipped with a horizontal 5-nozzle gas injection system and an omniprobe parallel to the FIB column, which is at 55 degrees with respect to the vertical SCM. I do not have the statistical data, but as I understand it, horizontal gas nozzle systems are not the norm, and they come with their own challenges when it comes to spatial freedom. In this talk, I'll be describing a method to prepare a lamella for heating chips using this specific geometry. So you can see the view of the inside view of the SEM chamber here. So what is the problem exactly with this geometry? Well, so with the grid design, the region of interest is not located at the top of the grid, FIB half grid. This means that you do not have easy access with the horizontal gas when trying to attach the lamella to the grid. With a regular cross-sectional lamella, you have the freedom to do so because of the grid design and also the orientation. You place the lamella on your FIB grid standing upright. Not so simple with the bulkier Protochips grid / chip. I'll be using those two terms interchangeably. So how do you attach your lamella then to this Protochips grid? So I'll be presenting a working guide on how to get a lamella attached to the heating chip. We'll go through the standard steps to make a standard cross-sectional lamella, followed by the secondary steps necessary to get this lamella on a Protochips grid. The idea is to snatch it from a regular FIB half grid and reattach it to the Protochips grid. The reason I propose this method is the impossibility of removing your lamella in a position that would allow you to directly attach it to a Protochips grid. So speaking of a few different flavors, so this talk is just only about the heating chips. And so you have three choices of substrates for these, which is carbon, silicon nitride, or nothing. So in this case, we'll be using the uncoated grid as we don't have a need for anything. What they all share between the different models is they all have this 3x3 grid of 8 micron wide holes. This is where we're going to be observing the samples. So knowing the size of the hole, we take this into consideration in the size of the lamella we're going to fabricate. A standard lamella could be around this size, that is 8 microns. So we want to modify that because we'd be placing it on the edges and it wouldn't be as safe, as easy to land. So we want to have extra width so that we'll be supporting our grids on both sides. Benchmark, that is around 15 microns. Keep in mind that you'll be cutting away your lamella after attaching it to a grid, but so that should be minimal if everything goes well. This is what the setup looks like in the chamber. These views will be placed in the corner of every slide to help you follow along the steps to show you how we're setting up. I give credit to a previous Protochips presenter who gave me this idea. We start with the usual protective coating, which is done with a platinum precursor here. This is done in 2 steps. First with the electron beam to prevent damage to the surface, and second with the ion beam. I usually make mine rather thick because I find it gives me more freedom during that final polishing step. It makes it less stressful. This way I can always have some platinum that remains on top of the lamella, which helps me with identifying interfaces, and it's just all around safer to keep that topmost surface interested in. Now, once we have this, we then mill trenches. Trenching apparently is not a verb, by the way, as far as I know. So we mill trenches. This is done with as much current as your scope is able to produce to speed up the process. I always mill a relatively large opening on the side for easier access with my probe. I tend to keep using them for a very long time, so I'm sometimes using a larger tip than I would like to. So this extra opening lets me bring it in safely. I follow this up with a rough polishing, which we can see here. And then here we flip the stage back to 0 degrees to start freeing our lamella from the substrate. I make my left cut as close as possible to the wall so that I can keep as much of the lamella as possible. I also mill away a bit more in the corner, as you can see on the bottom right corner, over here. Here. As in the past, I've had it with the lamella sticking there as I'm trying to free it from the substrate. We then bring in the probe to attach to the lamella. I typically attach to a point a bit lower than what is shown here to have a more secure connection, but this worked out just fine also. To remove the lamella from its substrate, we simply have to cut away the remaining portion on the left. I then usually lower my stage before moving my probe, as I trust that movement a little bit more. We can then attach our lamella to the grid. This is indeed a dirty grid you're viewing, but this is just fine for the purpose of this job, where I'm going to be removing it very shortly from it anyways. So I simply clean the edge of the grid, as you can see by the sharp sidewall here, which allowed for a secure bond with the lamella. So we start the polishing process. You have options here. I like to prepare a viewing window that is around half the width of the lamella sample to view, and allows me to have a solid frame around it. I do not know yet if this is better for this application with the Protochips grid. I'll be playing with this geometry in the future to see if there are any differences. If anything, it means less work, so the lamella is produced, it's finished faster. I like to mill evenly on both sides so that my lamella is located in the middle of the frame. This is again for the stability. So I'd be milling, as you can see on both this page and the next, I'll be tilting about 2 degrees with respect to the FIB view. And so I like to hit both sides. Moving on to more polishing. So every step prior to this was done with the maximum 30 kV of the scope, but we now switch to 5 kV. This is done to reduce the damaged amorphized layer. And so this is done again on both sides to have everything as neat as possible. So now we have a fully ready lamella. This could be viewed in the TM. It's absolutely ready. But so we want to grab it now. We want to snatch it away from its home. We want to think about where it is going. We're going to have to lay it against the Protochips grid, going from north to south. If you're looking at the view in the SEM. So we want to place the probe as much as possible on that north, the top side of the lamella. If we don't, we're going to run the risk of puncturing the substrate as we approach the Protochips grid substrate. So we'll see this in a few slides. So once we're happy with our connection, and we want to make it a really good one, again, because we're going to be applying pressure, so we move on. We really need this to be sturdy. As you can see, my connection has a lot of excess platinum, so I really make sure I have a very good connection. It's very important. So what we are looking here is the 6-degree tilted SEM view of the Protochips grid loaded vertically. So I use a vertical holder with a clamp. You could use a slotted vertical holder with a set screw. You just need one to have one of the right size. This slight angle allows us to keep both our eye on both the SEM and the FIB view, which is very important as you're trying to connect this. So you've managed all of this. You've prepared TM lamella, and now you're trying to bring it to the surface of the Protochips grid. So this is easily the most critical part of the process. Because of the geometry, you're going to have to push your lamella against the substrate, as I've mentioned before. You're going to have to win about 12 degrees. So you have to have submicron precision with your 3-dimensional positioning, as you need to be correctly on your viewing area above the hole. So you need to start welding this. So you press it against the substrate, and you start with, you can either do corners or sides. I've always done corners, but as long as you get some material there, you're gonna have a weld. You will need to do the last one, obviously, after cutting away your probe. You want to be careful with cutting away your probe, but it is not so critical. I have actually cut through and then started milling the substrate, and I still had a viable chip and sample. But just don't overdo it when you're trying to cut away your probe. Go slowly, and you have an expectation of the time it should take. And voila, so you now have a viable lamella attached to your Protochips grid, ready for viewing. As you can see again on the sides, on the corners, but this is not going anywhere, and this is what we want. In summary, if you're going to need this technique, think about the following. So take time to consider all the steps and prepare everything in your software in advance, so your drawing file. You'll probably have to make adjustments, but just thinking about the process in an abstract way will help you solidify the technique. That being said, there's nothing like practice. So do try first on a cheap substrate, be it a defective grid or just about anything you can lay your hands on. As long as there's a surface, you can glue something to it. Your first attempt might work, it might not, but at some point you will fail. So just keep track of your mistakes and fix them. And also make sure that your multiple component instrument is running properly. Do not forget to have a nicely shaped probe. In my case, I experienced issues with the GIS during the time of making this, which caused lamellas to drop as the welds were too weak. So everything needs to be correctly working for this. And with this, I will say thank you and show you a little something. So this is also what can happen and probably will happen to you at some point if you make a few of these. Thank you.